studying the way in which a dielectric material responds to oscillating electric fields and how that then relates to propagation of electromagnetic waves in that medium. And so we're looking in particular at linear response, where the polarization, the electric dipole density, is linearly proportional to the field in the medium, with the proportionality constant, the electric susceptibility. And for the moment, we're taking this to be a scalar. Okay, we're assuming our medium is isotropic and responds in the direction of the applied field. And the way we can model that is by thinking about the molecular constituents in the material, for which there is some molecular polarizability, such that the response amplitude at that frequency is proportional to the electric field amplitude at that frequency. And that proportionality constant is called polarizability. So generally, the relationship between chi and alpha is fairly complicated because of, as we discussed, so-called local field corrections. But when we have a sufficiently dilute sample, then we can write a simple model and just say, well, there's some number density of molecules, atoms, whatever this dilute sample is, and we just multiply the polarizability times the density, that gives us susceptibility. And thus the dielectric response, the permittivity, is then given as such. And from that we can in principle calculate the complex index of refraction, okay, at that frequency. Now again, the point here is that we're looking at the response at a particular frequency. So we should be thinking about this, as we will in a moment, as the response in the frequency domain. That is to say, we can think about this as the Fourier transform. They're one and the same thing. We study frequency, which doesn't exist, where we have an infinitely long wave train, because that is a basis for expansion of a physical signal. So when I write this in the frequency domain, I can either be thinking about this as I have a wave which is oscillating at that frequency, and this is the complex amplitude associated with that frequency, or equivalently, I can think about this is my EFT. I can be thinking about this if I had a superposition of these, then the signal would look something like the integral of all the positive frequencies This is the same thing as this when I now think about this as having multiple frequencies. Okay? Of course, they're not exactly the same. This thing has slightly different units than this, but conceptually, they are the same thing.
So what are those limits that you put on the...
Well, I put this from 0 to infinity because this is just a positive. If I write this now as this plus its complex conjugate, over 2, which is the real part, then I have the integral from minus infinity to infinity, right, which is the Fourier transform. So the positive frequency component is the complex amplitude for multiple frequencies. Of course, there's a funky factor of 2, which really shouldn't be there. It really should have been twice the real part, which is what's been written here. Okay, so we looked at a particular model which gets us a long way in understanding the physics, the so-called Lorentz oscillator model, in which we think about the bound charges that make up this dielectric as being harmonically bound on a spring with some natural resonance frequency omega naught and some damping rate gamma. And from that, we were able to derive the polarizability, as written here, the complex polarizability by solving the steady state behavior of the damped simple harmonic oscillator. And from that, we can get the susceptibility. Now, here I've generalized things a little bit. I've allowed myself to say maybe there's not just one resonance frequency, but my molecules have many different resonances at which they will absorb, right? I mean, if I had a molecule or an atom, of course we know, due to the stationary states or the eigenstates of the bound states of the molecule, there are many different absorption resonances in the molecule. Of course, this was seen empirically before the invention of quantum mechanics, and the way it was dealt with was to put in a fudge factor, to say that, well, there's some strength of the resonance, so-called oscillator strength. And we just weight each one of these complex resonances associated with a particular damped harmonic oscillator, which has a particular resonance frequency and damping rate by some strength F. There is a relationship for that we get from quantum mechanics in terms of the actual dipole matrix elements, if this is, we're inducing an electric dipole, et cetera, et cetera. But in the moment, right now, it's just a fudge factor. Okay? Now, I should say, and something we're going to study in homework, that as we discussed last time, the real part of chi is related to the dispersion of the wave, and the imaginary part is related to the amount of energy that's transferred between the wave and the medium. When chi, the imaginary part of chi is positive, as we have for the damped simple harmonic oscillator, so here's, of course, it's related to the imaginary part of alpha, then we have absorption, strong absorption, as the material absorbs the light. That's to say, work is being done on the charges by the fields. And that would correspond to a positive oscillator strength. In principle, as we discussed, say, for example, if we have a laser, we can also have the opposite be true. We can take energy from the medium and put it into the fields, in which case we have an amplifier. And we can model such an amplifier by making F negative. So if F is greater than 0, if the oscillator strength is greater than 0, then we have an absorber. And if the oscillator strength is negative, then we have an amplifier. And that would just look, the dispersion relations would look just the opposite. We just make F negative. Okay? So we're going to study in homework some very bizarre and interesting properties that happen in the propagation of light in an amplifying medium away from the gain line. Talk about that in a little bit. Okay? All right, so we then turned our attention. We have this description of saying, let's look at the propagation of a pulse through a dispersive medium where we have, imagine, for example, this is the input phase to our medium at z equals 0. We're just going to treat one-dimensional propagation, ignoring the transverse spreading of the beam, where we have some signal that we're putting in at some time t, and it then propagates into the medium for z greater than 0. And so we can write down a formal solution to that instantly by using Fourier analysis, because we can take our initial signal, break it up into its Fourier components. That represents the signal at the input phase at z equals 0, which I've written here in terms of the positive frequency component. And then we know then what the solution is for each frequency component. Each frequency component propagates as a plane wave with a wave number that's related to that frequency through the dispersion relation. And then we just add up all those plane waves, weighted by the amount of amplitude there was at that frequency, which isn't changing in this linear medium. All right, so that's the formal solution. And we were looking at the problem of quasi-monochromatic pulse, where our input signal was some pulse amplitude that modulated some frequency. So this is not the resonant frequency of the material. Omega naught is the what we call the carrier frequency. Okay, and this is the pulse envelope, which is slowly varying with respect to the period of oscillation. And so we have some pulse envelope here such that if I were to then Fourier transform this and look at the distribution here, that this thing has a spread in frequencies that's much, much less than omega naught. And so if I look at the Fourier transform of this signal, it has a very narrow peak centered at omega naught. That's the positive frequency component. Of course, there's an equal symmetric. In this case, I have a real function, so it's symmetric at the minus omega naught. Okay? And so in the quasi-monochromatic approximation, there's very little, this tail has almost no support on the positive frequency axis. And so I only have to integrate over this centered at omega naught. So our signal in that case, what is that is to say, the signal at some later position z, that is to say, the wave propagation downstream, was equal to the real part of the integral minus infinity to infinity. Not omega z minus 8. Okay. So then, because this thing, if we make the change of variables and we integrate over the difference between omega and omega naught, since this thing falls off very quickly, we can extend that integral from minus infinity to infinity, because it doesn't do much out here, just for simplicity. So this is approximately equal to the integral minus infinity to infinity, the integral over that difference between omega and the resonance frequency, d to the I k tilde omega naught plus delta minus delta t. Okay? So, let's consider, although we can do it more generally, but let's just focus our attention for the moment. Let's suppose that we're in a transparent band where K is real. Okay, so there's no, we're ignoring the imaginary part of the index of refraction. So let's focus on that for the moment. What we discussed is then, since the support, this function is peaked near delta equals 0 and has very little extent compared to omega naught, we can do a Taylor series expansion of this function near delta equals 0, because the integral is non-zero everywhere else, except where delta is very small because of the narrowness of this peak, because we have a quasi-monochromatic pulse. So this was approximately then equal to in which case, if we keep the terms to lowest to first order, in delta, then this is equal to the real part integral e to the minus I omega naught. I'm sorry, e to the minus I delta t minus the derivative of this z e to the I k naught z minus omega naught t. Where k naught is equal to k at omega naught, so omega naught over c and at omega. So, what we see here then, remember that the amplitude itself if we take the inverse Fourier transform over some dummy variable delta was equal to this. That's the inverse Fourier transform of this function. So what we have is the inverse Fourier transform evaluated now, not at t, but at t minus this. And this is 1 over the group velocity. So the group velocity of the pulse is defined as the derivative of omega with respect to k. So 1 over the group velocity is dk of omega with respect to omega at omega naught. That's the group velocity at the carrier frequency. And so the solution that we find is that this is equal to the pulse envelope evaluated now at t minus z over v group times the cosine k naught z minus omega naught. And that's the solution to this order of approximation to first order in delta. And that solution shows the behavior whereby I start with some pulse envelope, which has some carrier. And later, what happens at some downstream is that the pulse propagates. The peak of the pulse travels down a distance z, where z is equal to d group times t at some later time. And the carrier wave travels at the phase velocity. So the phase velocity is omega over k, not the omega d of k, which is c over the index of refraction at that frequency. Is everyone clear on that? Now, one of the things, I guess, okay, before I get into that, I want to say one other thing. What is the effect of this neglected next order correction in this expansion around delta equals 0?
Would it cause a widening of the pulse?
It does indeed. So let's look at this. So the effect of the second derivative of k with respect to omega. Well, that's the derivative of dk d omega, which we said was 1 over the group velocity. Which is equal to the derivative of the group velocity with respect to omega divided by minus squared. Right? So, the effect of the second derivative is what we call group velocity dispersion, GVD. It says that, well, if I have a spread in frequencies, each little frequency piece, with if I go back here, I don't have a single frequency, I have a spread in frequencies. Each little frequency band has its own group velocity, even within this narrow band. Which means each little frequency band will travel, the pulse will travel at a slightly different speed because the group velocity is not fixed at omega naught, but is spread over the range of frequencies contained within this pulse. Some of those colors will travel with a faster group velocity, some of those colors will travel at a slower group velocity, and then the effect is to cause a spreading of the wave packet. So whereas in vacuum, an electromagnetic pulse does not spread, okay? Unlike in quantum mechanics, where you get spreading of a wave packet, in electrodynamics, because of the relationship between omega and k, which is linear, that means that you have a constant speed, c, a pulse in vacuum does not spread longitudinally. If it goes in a dielectric, it can spread, and the amount by which it spreads depends on the second derivative of k with respect to omega. So we have a problem for that in homework to look, for example, at pulse propagation in optical fibers and how group velocity dispersion limits the rate at which you can transmit information on an optical fiber, because, well, if you try to put a bit in a pulse in a certain time window, eventually you're going to bleed into one another. Okay. The group velocity itself, if we look at the group velocity, as a function of omega, well, that's the derivative k is equal to n times omega over c. So this is then equal to 1 over c n of omega plus omega n. Okay. So we can define what we call the group index of refraction as the ratio of c to the group velocity. Unlike the index, which is defined in terms of c over phase velocity. This is what was called the group index. And that then is equal to, I'm sorry, this is 1 over, pardon me. Because then this is equal to n of omega. So, you may remember from your previous studies that it's quite often the case in certain kinds of media, in certain material, that the index of refraction itself is less than 1. And, for example, in a plasma. And then the phase velocity is greater than c, right? And then one says, well, that doesn't really matter because no information is carried in an infinitely long wave train. I don't know, because it's infinitely long, there's sort of no beginning, no end, no information was ever carried in that modulation of the phase. But the group velocity, then, well, how big is that? Its relationship to c is the group, related to the group index. So as long as this quantity is greater than 1, then the group velocity will be less than c. Well, is that always true? Actually, the group velocity can be greater than c. In fact, it can even be negative. So what the heck is going on? How do we talk about then information and the causality associated with being able to transmit information within the constraints of Einstein causality? And that's the topic that we want to take up now. The relationship between causality and material response. In order to do that, we want to discuss some general ideas relating to what is called linear response theory. Something that is well known more in the engineering community than it is to a lot of physicists. Let me just explain what I mean. Let's say I have a black box. Okay? And there it is, it's a box, it's black. Meaning we don't know what's inside it. But what we do know is that we put some signal in and we get some signal out. Okay? And that signal, say, is a function of time, and the output signal is some function of time. And there's some relationship between these two things, which is linear. And that response function we'll call G. So what do I mean by that? Well, what I mean to say is that if it's a linear response, then the output depends on the input in a linear way. Now, I might write that more generally in the following sense. There's some doesn't necessarily have to be instantaneous response. So the response, the signal that I get out at some time t, can depend on the whole history of the signal at some other times. And this function g tells me how to transfer the input signal to the output signal. Now we might want to demand certain other things other than linearity from this response function. Typically, we might be thinking about so-called stationary response, meaning that the nature of how this thing responds doesn't depend on the origin of time. So it's doing the same thing whether I do it today, tomorrow, in a year. Okay, so if it doesn't depend on the origin of time, that means that this only depends on the time difference between t and t prime. We don't have to assume that, but we'll restrict our attention to that. The other thing we want to assume is causality. That is to say, the signal at time t doesn't depend on what the input was doing in the future of t. It only depends on what it was doing in the past of t, which means that when thought of as a function of tau, this is equal to 0 if tau is negative. Okay. So these simple constraints says a lot about the nature of this response function. In particular, we can see what those constraints are by looking at this problem by taking its Fourier transform and looking at its response in the frequency domain. If we look at this in the frequency domain, we have the following. So we have written, according to our stationarity assumption, we have this relationship between the input and output signals, which says in the Fourier domain, the Fourier transform, yes?
Since we have a causality restriction, can we just change that to 0 to infinity?
We can. I mean, well, it only goes up to time time t, because beyond that, this is negative. But right now, I just want to leave it general with this property. Okay? Because we're going to see how that constraint works out. If I look at this in the Fourier domain, we know that the Fourier transform of this, well, this is the convolution of two functions. The Fourier transform of the convolution is the product of the Fourier transforms. So one thing we see, just generally speaking, causality or not, is that the response function in the frequency domain is a kind of frequency filter. That is to say, there's some frequency dependence of this G, and to get the output frequency dependence of the signal, I just take the input and I multiply it by it. And I can weight the input by output, and that's it. And then I can take the inverse Fourier transform. Get that. Okay. But now, we have causality. Causality says that this thing is equal to 0 when this is negative. Well, what that means is that g of t itself is the same thing if I multiply g by a step function. So I'm defining the Heaviside step function, theta, as the function which is 1 when its argument is positive and 0 when its argument is negative up to b. Okay? So that's what's known as the Heaviside step function.
Any particular history behind its name? Why Heaviside?
Got me. Can't tell you. But we can, your guess is as good as mine. Probably pretty darn good. So what does that say? Well, it says that if I were to ask now about the frequency response of the system, the black box, that there is a relationship now that the Fourier transform of G must be equal to the convolution of the Fourier transform of the step function with itself. Right? Because if the function is the same thing, whether I multiply it by a step function or not, then in the frequency domain, it must be the same thing if I convolve it with the Fourier transform of that step function. And this puts constraints that are known as the Kramers-Kronig relations. And it's what we want to study in the context of material response. But it's more than just electromagnetism. This comes up everywhere. If I'm looking at, for example, a scattering problem, where my input and output here now, as I put in some, I'm sending some high energy particles at a target, and I want to know what the scattered amplitude is. Again, because if I have causality, which I do, then that puts constraints on that scattering amplitude. It will tell me something about what the bound states are, for example, within that. So this is not just about electromagnetism. It's about whenever I have linear response, and it's an extremely important tool that we use all the time in many different fields of physics. All right, let me grab my notes here and use this now as our launching point to discuss, to get some more intuition about what's going on. This G of t, so notes. G of t is known as the Green's function. Why is it known as the Green's function? Well, there's some differential equation which typically relates a linear differential equation, in this case, which relates the input to the output. And G is the Green's function of that differential equation. Let's look at that in a little bit more detail. So how do I understand what's an interpretation of G? Well, G is also known as the impulse response. Why do I say that? Well, let's suppose that the input signal itself was an impulse. I'm just going to put in a signal that's a very short pulse, which we'll write as a delta function at time. Okay, so that's my input. What is the output in that case? Well, there it is. I'm integrating my Green's function here. Oh, I'm sorry. That's all screwed up. Back up. Sorry. Do something wrong. S of t prime is delta t prime. Thanks to that. Okay, that's my input. Integrate over t prime, I get the Green's function. So the Green's function can be interpreted as the output when given an input that is a delta function. That is what we call the Green's function of the differential equation. It's what we studied earlier on at the beginning of the semester, not in the context of a time response, but in terms of space response, and we looked at the Poisson equation, and we broke up the charge distribution in terms of a bunch of point charges that were delta functions, then added them up. Because I could take, the reason is by linearity, because this is linear, that's essential, we have the principle of superposition. So that means I can take an arbitrary input signal at time t as a weighted sum or integral of delta functions. So it's saying the signal itself as a function of time, well, it's just impulses at all different time intervals with a certain height given by this. And thus, the output signal is just the superposition of inputs with the response for each delta function. Okay, in fact, let me call this instead of T naught, let me call it T prime. Then the formulas look exactly the same. That means the output is the weighted sum, which we're writing as an integral, of that strength times G, because each delta function gives rise to a G. So that is the picture you should have. That's what the Green's function means. It's not just a math thing. It's just the principle of superposition. Each impulse gives rise to a Green's function, and then we weight that by the strength of that impulse. All right. So, let's see. So, we ultimately want to, the problem that, oh, I shouldn't have erased that. Let me write it back up over here. Yeah. Here is the input-output relation that we care about for the electromagnetism problem at hand. We want to know what is the dielectric response. That's to say, how much polarization do we get for a certain amount of electric field? Our transfer function is the susceptibility. Or written in the time domain, the amount of polarization we get at a particular time is the Fourier transform, inverse Fourier transform of the susceptibility function involved with the inverse Fourier transform of the susceptibility function. And based on causality, we want to put constraints on what these guys are and learn something about that. Perhaps can we get group velocities that are negative or faster than the speed of light than we need. So to do that, we want to study the properties of these guys based on the causality constraint. All right. I want to use this board again, so I'll see it clearly. All right, so let's look at the constraints of causality on a general Green's function. For that, we're going to turn to some fairly advanced mathematics of functions on the complex plane. Something I hope you've seen in your math methods course. You guys all take 466, or at least you cover analytic functions, contour integration, all those goodies? All right, I assume you have. So, let me remind you of some things. So, what we're interested in here is we have our Green's function and its Fourier transform. To where this is 0 when t is negative. Tells me. Okay? In order to deal with this and ask what this means, how does this constrain, one of the ways we can think about this constraint on our transfer function is to do an analytic continuation. That is to say, we're going to treat this function on where a complex plane where now we're going to allow the frequency itself to be a complex number. This integral is on the real axis of the complex omega plane. Okay? So we have the complex omega plane where we're going to use the notation for simplicity where we use the prime as the real part and double prime as the imaginary part. Okay? Here's the complex omega plane. We're doing the integral over the real axis. Okay, from minus infinity to infinity. Now, we know from, recall, for a complex function on the complex plane, that if I look at an integral along any contour in the complex plane, if I have a closed contour, that integral is 0, unless there are so-called residues of the function, right? This is equal to 2 pi I times the sum of the residues of the function. What are the residues? You recall the residues are the places when I expand my function in a Laurent series that can involve, and going from minus infinity to infinity, the residues are the places where this thing blows up at when the ends are negative. Right? All right, so what does that mean here? Well, let's look at our Fourier transform now. So let's consider the integral over some contour, which I won't yet specify, of this function somewhere in the complex omega plane. Ultimately, we're interested in its value on the real axis. But let's look at it for an arbitrary complex omega and write this now in terms of its real and imaginary parts. Where I've written omega tilde in terms of its real and imaginary parts. Well, this tells us something about how I can express this real response function, which is the integral over the real axis, in terms of a contour integral with respect to the entire complex plane. Because I can say the following is true. Let's look at the integral along this contour from some minus omega to plus omega in the limit that omega goes to infinity. Okay? So this contour integral, you got to draw it that way. Is equal to the integral over that part of the contour. That's the thing that is equal to g of t, plus the integral over that semicircle. So, what can we say about that? Omega double prime is positive indeed. Thank you. Okay, so, okay, yeah, good. Sorry, got myself confused about the sign. Say we tried to do that. All right, this is correct. And now we can say the following thing. Suppose tau is less than 0. Okay? Let's consider the evaluation of this integral, which is not written correctly. Now it is. When tau is a negative number. Tau is a real number, and it's negative. Well, as we take the limit that this semicircle goes off to infinity, as the limits of integration go into infinity, then everywhere on this curve, the imaginary part is positive, as Aaron very importantly pointed out that this had to be the right sign there. So if tau is negative, and we've closed this in the positive part of the complex plane, then this goes to 0 as this goes to infinity, which it does when we take the limit that we move this semicircle all the way off to infinity. Which means that the thing that we want to calculate is equal to this closed loop integral. So, what we have here is the following. G of tau, the thing we want, is equal to the closed contour integral in the upper half plane of the analytically continued G. When tau is negative. Similarly, I could have closed this contour integral in the other direction. In which case, what we find is that this thing is equal to this when tau is positive.
So let's just play omega in this case. Is that right?
That should be a tilde. It's all tilde. Okay. So we get two different ways of calculating this, either when tau is positive or tau is negative. However, so far we said nothing about causality. What we know is that this is equal to 0. When tau is negative. Which means that this has to be 0 if we have a causal response function. But we just said that if we do a closed loop integral according to the right-hand rule in the complex plane, that that's equal to 2 pi times the sum of the residues. And the residues are related to the poles of this function. That's to say, the places where it blows up. And since this is 0, what that says is there can't be any residues in the upper half of the complex plane of this function. If it's a causal function, then g of tilde of omega has no poles in the upper half of the complex omega plane. So we've learned one important constraint. If we have a causal response function, then all of the poles must be in the lower half. Yeah.
So I forget, but by like poles and residues, you mean like any order?
All of them.
Okay.
That's right.
Okay.
It doesn't matter. The residues, so the residue, so if Zj is a nth order pole, then the residue at Zj is equal to the limit Z minus Zj to the power n f of z.
I said it's in my pocket.
Is that, let's see, how does that go again? Yeah, it's limit of z. That's the definition. Okay, so if we have a causal response, then if there are poles, they are in the lower half plane. And we can calculate the response function by looking at just those residues in the lower half plane. And the function will be 0 for tau negative. Let's do an example. By the way, did you cover this in 466? Yes, good. Hopefully you took 466.
Do we care about any cases where there are poles that cancel, or residues that cancel in the upper half plane?
Residues that cancel in what
In
sense?
the upper half plane. Well, they can be positive or negative.
Right.
And you're getting all of them in the upper half plane, so they could cancel.
It's a good question. I know that one says that the function must be analytic in the upper half plane. G of omega must be analytic in the upper half plane if it's causal. That's a good question. I don't know what would happen to it cancel. I think I'd have to think about that a lot more carefully. My guess is that one could do other contour integrals to prove that there just can't be any poles, period. But I'm not, that's my guess, but I've never actually encountered that. I don't know the answers. Okay, so let's look at the example of our response function that we care about in our context according to Lorentz oscillator model. Let's say we have, so we wrote this as omega p squared, sum over this, the oscillator strengths, omega squared minus omega j squared minus I omega j. Yeah, right? This is over 4 pi, but it doesn't matter. It's just the overall constant out front. And I did get this backwards. Okay, question. First question. Where are the poles of this function? Well, the poles are the place where this goes up. So the poles are the roots of the denominator. So the poles are the solutions to the equation this plus I omega gamma minus omega j squared. Say this equals to 0. Just multiply that by a minus sign. So we can.
Why did the sign change?
Oh, because I wanted to write it as a quadratic equation in omega. I just multiplied everything by 3 by minus. This is, now I can just use the quadratic formula. And I didn't want to have to carry around an extra.
And should that be omega, not omega j? Multiplied by gamma?
Yes, it should be important. Thank you. Now it looks like a quadratic formula. So the roots of this, there are plus and minus roots. Minus b plus or minus the square root of b squared
Wait, where are we solving from?
minus 4 times a times c over 2a. We're solving for omega, the roots of that formula. Okay? So here are the roots. Omega j plus or minus is equal to minus I equal to 2 plus or minus something I'll call omega sub j plus omega sub j is equal to the square root of the resonance frequency minus delta squared over 4. Okay, so those are the roots. Those are the poles. And I kind of drew them where they are. They're on the minus, they have a negative imaginary part. The imaginary part's negative. And then its real parts are symmetric which it must be because the overall function was real, and we know that we have the positive and negative frequency components appropriate. Let's calculate, and we'll do this as our last thing, and then we'll continue to derive the Kramers-Kronig relations next time. What is the real response function, chi, as a function of tau? Well, according to the formula that we have, this is 0 if tau is negative. And if tau is positive, we have this guy extended into the complex omega plane. But that's just related to 2 pi I times the sum of the residues. Now this is in the wrong direction. This is the left-hand rule. Because there is an orientation to the contour for it to be 2 pi I. So it's equal to minus 2 pi I times the sum of the residues. All right, so what are the residues of this guy? Well, they're the residues of this function. Okay, so it's minus I times the residues, sum of the residues, or the residues of that. Okay? So there's 2 poles and thus 2 residues. There is a residue. So let me write out again. Chi tilde is equal to omega p squared over 4 pi times omega minus omega j plus times omega minus omega j minus. Overall minus sign, because I factored it out. It's omega squared, right? These are the roots. And then I have to sum over all. Of the poles. I just wrote the denominator out, factoring that quadratic factor in terms of its roots. Okay? So, there's a residue at omega j plus, which is equal to minus p squared over 4 pi, the oscillator strength, j plus, minus I, j plus. That's the residue of that function at j plus. Plug in, get rid of that, plug in j plus, that's the residue. And then there's this one at j minus, which is the same thing, but now j minus minus j plus e to the minus I. We'll make it j plus. All right, let's put it all together, and then we'll call it quits. And I'll review this next time. response function, which is the susceptibility to the function of tau, is thus equal to we have I times the residues, so that gives us sum over J, Fj. I e to the minus J plus tau over J plus. This I is that I. And then the other residue. When you simplify that, you get the following expression. So, the Green's function, or the response function in this case, is the following. It is a damped oscillator with a frequency, well, for each J, a frequency omega J, which is the square root of the resonance frequency. So, what does this mean? Remember what we said is that the response function is the impulse response. What are we doing? We have a harmonic oscillator. I have a ball-peen hammer. Maxwell. Bing. It rings. It rings and it oscillates at a frequency which is, here I've assumed under damping. I've assumed that the damping is such that that the resonance frequency squared is still bigger than omega squared 4. It rings with that frequency and it damps. That is the Green's function. If I wanted to know how my driven oscillator responds to an arbitrary function, all I have to do is convolve this damped oscillator with the force. And that will tell me how the function responds to an arbitrary driving function. Okay. Review your complex analysis, and we will continue this next time.
Next